Hi everyone, this is Alex. Today we are going to learn about implicit differentiation. Look at these two equations. Y equals 3x squared plus 1 on the left, y plus y squared plus xy equals 2 on the right. Both describe a relationship between x and y, but there's a big difference. On the left, y is alone. We can compute it directly. On the right, y is mixed in with the x everywhere. We cannot isolate it easily, sometimes not at all. Today's question is, how do we differentiate the implicit ones? And here's the good news. You already know how. We just need to be more careful with one tiny detail that has been hiding in plain sight. Take a look at the box rule for power. We say the derivative of the box to the n is n times to the box to the n minus 1 times box prime. We used this rule dozens of times already in chain rule, in product rule, everywhere. Now let's apply this rule to something extremely simple. The derivative of x squared with respect to x. What do you get? Most of you will say 2x, and you're right. But watch what happens when you write out every single step of the box rule. The box is x, so by the rule, we get 2x times the box prime. And what is the box prime? It's the derivative of x with respect to x. That is dx over dx. Now, here's the trick. dx over dx equals 1. Anything divided by itself is 1. So this term quietly disappears, and we are left with just 2x. That's the answer you've been getting all along. But notice, the box prime was always there. You just didn't see it because it equaled 1. You've been multiplying by 1 every single time without recognizing it. Now, this is where it gets interesting. Second case, what if we are differentiating x squared, but this time with respect to t, not x? So, d over dt of x squared. The box is still x, and the rule still says 2x times box prime. But now the box prime is dx over dt, and dx over dt is not equal to 1. We don't know what it equals. X and t are different variables. So this term stays. Our answer is 2x times dx over dt. Third case, and this is the one that matters for today. What about d over dx of y squared? Notice the variable inside the box is now y, but we are differentiating with respect to x. By the rule, the answer is 2y times box prime. And the box prime here is dy over dx. Is dy over dx equal to 1? No. X and y are different variables, so this term does not cancel. It stays. Our answer is 2y times dy over dx. So here's a big idea. Implicit differentiation is not a new method. You are using the box method completely, without skipping the last step. The box prime is always there. The only question is whether it cancels into 1 or whether it stays. When the box matches the variable you are differentiating with respect to, like d over dx of x, the box prime is 1 and disappears. When it doesn't match, like d over dx of y, box prime stays in your answer. That's the entire secret. Let's apply this idea to our first example. We have x squared plus y squared equals 16, and we want to find three different things: dy over dx, dx over dy, and dy over dt. Now you might be thinking, wait, three different derivatives from the same question? Yes. And once you understand the box prime idea from the previous slide, all three will feel completely natural. Let's bring up the box rule on the side because we are going to lean on it heavily. We start with dy over dx. So we differentiate both sides of the equation with respect to x. That gives us d over dx of x squared plus y squared equals d over dx of 16. Now break it term by term. D over dx of x squared plus d over dx of y squared equals 0. The derivative of 16 is 0 because 16 is a constant. So far so good. Now apply the box rule to each term, but don't skip the box prime this time. The derivative of x squared is 2x times dx over dx. The derivative of y squared is 2y times dy over dx equals 0. Here's where the magic of the previous slide kicks in. dx over dx equals 1, so it disappears. That term cleans up to just 2x, but dy over dx, highlighted right there, stays. It does not cancel because y is not the same variable as x. This is the term we are actually solving for. So now we have 2x plus 2y times dy over dx equals 0. Move 2x to the other side. 2y times dy over dx equals negative 2x. Divide both sides by 2y, and we get dy over dx equals negative x over y. That's our first answer. Notice something interesting. The answer has both x and y in it. That's normal for implicit differentiation. The gradient depends on which point you are at on the curve, and that point is described by both coordinates. Now let's do the second one, dx over dy. Same equation, but this time we differentiate with respect to y, not x. Watch how the roles flip. d over dy of x squared plus y squared equals d over dy of 16. Break it apart. The derivative of x squared with respect to y is 2x times dx over dy. The derivative of y squared with respect to y is 2y times dy over dy equals 0. And here's the flip. This time dy over dy equals 1, so it disappears, but dx over dy, circled right there, stays. Same logic as before, just with the roles of x and y switched. So we have 2x times dx over dy plus 2y equals 0. Solve. 2x times dx over dy equals negative 2y. Divided by 2x, and we get dx over dy equals negative y over x. Look at the two answers side by side. dy over dx is negative x over y, and dx over dy is negative y over x. They are reciprocals of each other. That's not a coincidence. It follows from the fact that dy over dx and dx over dy are inverse rates of change. So both derivatives comes from exactly the same equation, but the box prime that survives is different depending on which variable we are differentiated with respect to. That's the whole game. Now the third one, dy over dt. This time we differentiate with respect to t, a totally new variable that doesn't even appear in the original equation. So watch what happens. d over dt of x squared plus y squared equals d over dt of 16. Apply the box rule. The derivative of x squared with respect to t is 2x times dx over dt. The derivative of y squared with respect to t is 2y times dy over dt equals 0. Now here's the key. Nothing cancels this time. Neither dx over dt nor dy over dt equals 1 because t is different from both x and y. Both box primes stay alive. Solve for dy over dt. Move the first term to the other side. 2y times dy over dt equals negative 2x times dx over dt. Divide by 2y, and we get dy over dt equals negative x over y times dx over dt. Notice something important here. The answer for dy over dt depends on dx over dt. That's because t is a separate variable, and the rate at which x changes with the t affects how y changes with the t. This idea, relating two rates through a shared question, is exactly what we'll explore later in related rates. Today is the foundation. Remember this moment. So 3 derivatives from one question. Same box rule every time. The only difference is which box prime survives. That's all implicit differentiation really is. Alright, next example. We have e to the xy equals x squared. This one mixes the implicit differentiation with the exponential rule from chapter 5.7. So it's a great test of whether you really understand the box method. Let me bring up our rule for e to the box on the side. Remember, the derivative of e to the box is e to the box times the box prime. And technically, times ln e, but ln e equals 1, so it disappears. So the question is, what's inside the box on the left side? The box is x times y. That's the whole exponent. So when we differentiate e to the xy, we will get e to the xy multiplied by the derivative of x times y. And x times y is a product, so we'll need the product rule inside there. Watch how this stacks together. Let's differentiate both sides with respect to x. d over dx of e to the xy equals d over dx of x squared. Left side, apply the box rule for e to the box. We get e to the xy times xy prime. The box prime is the derivative of the inside. Right side, the derivative of x squared is 2x times dx over dx, which is just 2x. Now expand using the product rule. E to the xy times x prime y plus x times y prime equals 2x. Writing the primes explicitly, this becomes e to the xy times dx over dx times y plus x times dy over dx equals 2x. And here it goes again, dx over dx on the left collapsed to 1. So the bracket simplifies to y plus x times dy over dx. Our equation becomes e to the xy times y plus x times dy over dx equals 2x. Distribute e to the xy across the bracket, e to the xy times y plus x times e to the xy times dy over dx equals 2x. Now isolate dy over dx term. Move e to the xy times y to the right side. We get x times e to the xy times dy over dx equals 2x minus e to the xy times y. Divide both sides by x times e to the xy, and our final answer is dy over dx equals 2x minus e to the xy times y all over x times e to the xy. Done. Notice how this example brought together three rules. Implicit differentiation idea, the box prime survives on y terms, the exponential rule for e to the box, and the product rule for xy in the exponent. All three working together in one question. Okay, this next one is special, y equals x to the x. Now stop and think for a second. How will we differentiate this? It looks like power rule, but power rule says the base is a variable and the exponent is a constant. What about the exponential rule? That says the base is a constant and the exponent is variable. But x to the x? The base and the exponent are both variables. Neither rule applies. So we need a completely different strategy. Here's a trick. Logarithmic differentiation. We take the natural log on both sides first. That turns the impossible looking x to the x into something we can actually handle. Take the natural log of both sides. ln y equals ln of x to the x. So ln of x to the x becomes x times ln x. Look what just happened. The variable exponent came down and became a multiplier. Now this is something we know how to differentiate. The left side is ln of y and the right side is just x times ln x, which we'll handle with product rule. Let me also bring up the ln box rule on the side because we will need it for the left side. Differentiate both sides with respect to x, left side, d over dx of ln y. Apply ln box rule, box is y, so we get box prime over y. Notice the dy over dx showed up because y depends on x. Same implicit logic as always. Right side, d over dx of x times ln x. Product rule, x prime times ln x plus x times ln x prime. X prime is a 1, ln x prime is just 1 over x. So we get dy over dx over y equals ln x plus x times 1 over x, which is just ln x plus 1. Now, solve for dy over dx. Multiply both sides by y. Then dy over dx equals y times ln x plus 1. But y is just given as x to the x. Substitute back, and we get our final answer. Dy over dx is x to the x times ln x plus 1. We started with something that didn't fit any of our differentiation rules. We took ln of both sides, which collapsed the impossible structure into a simple equation. Then we used the implicit differentiation. This technique is called logarithmic differentiation, and the key recognition pattern is whenever you see a variable raised to a variable, or complicated product or quotient with many factors, take ln first. It transforms the hard problem into one you already know how to solve. Hold on to this trick. The next example is going to push it even further. Alright, last example. And this one is the toughest one in the entire lesson. Y to the x equals x to the y. Look at both sides carefully. On the left, base is y, exponent is x. Both variables. On the right, base is x, exponent is y. Also both variables. Neither side fits power rule or exponential rule. Both sides are exactly the same situation we just saw in the y equals x to the x. So we use the same strategy as before, logarithmic differentiation. Take ln of both sides, bring the exponents down, and then differentiate implicitly. Take ln of both sides. ln of y to the x equals ln of x to the y. So the exponent on each side comes down as a multiplier. X times ln y equals y times ln x. Beautiful. The impossible problem is just now two products. Both sides are products of two functions of x, so each side needs product rule when we differentiate. Easy. Differentiate both sides with respect to x. d over dx, x times ln y equals d over dx, y times ln x. Applying the product rule, this becomes x prime times ln y plus x times ln y prime equals y prime times ln x plus y times ln x prime. And we can rewrite this as dx over dx times ln y plus x times dy over dx over y equals dy over dx times ln x plus y times dx over dx over x. Time for the family cleanup. Both dx over dx terms, one on the far left and one on the far right, collapse to 1. They disappear, only the dy over dx terms survive. After the cancellation, our equation becomes ln y plus x over y times dy over dx equals dy over dx times ln x plus y over x. Now collect dy over dx terms on one side, everything else on the other. Move dy over dx times ln x to the left and ln y to the right. Then dy over dx times x over y minus ln x equals y over x minus ln y. Divide both sides by bracket, dy over dx equals y over x minus ln y all over x over y minus ln x. This is technically a correct answer, but it has a fraction stacked inside the fractions, which is ugly. Let's clean it up. Multiply the numerator and denominator by xy. This clears all the inner fractions at once. So we have dy over dx is y squared minus xy times ln y all over x squared minus xy times ln x. There it is, the final answer to the hardest problem in this lesson. Take a step back and look at what we just did. We started with the y to the x equals x to the y, an equation that doesn't fit any standard differentiation rule. By taking ln of both sides, we transformed it into a clean implicit equation that only needed product rule, ln box rule, and the standard implicit logic of dx over dx disappearing while dy over dx survives. That's the entire lesson in one example. The box method layered on top of itself, applied carefully step by step, can handle anything IB throws at you. 11 examples, and notice we never once needed a brand new technique. Every single one came down to the same handful of moves. So before we finish, let me put it all together into 3 ideas you can carry with you. First, the box method has not changed. This is a big idea of the whole lesson. Implicit differentiation isn't just some new, scary topic. It's just box method you already knew, never skipping the box prime at the end. The box prime was always there. Today, we just stopped letting it hide. Second, dx over dx equals 1, so it disappears, but dy over dx stays. That single fact is the heart of everything we did today. When the box matches the variable you are differentiating with respect to, the box prime collapses to 1 and vanishes. When it doesn't match, like a y inside a d over dx, the box prime survives, and that surviving term is exactly what we solve for. Third, the algebra matters at the end. Once you differentiate it, the differentiation part is basically done. What's left is the careful algebra. Collect all your dy over dx terms on one side, factor it out, and divide. Don't rush this step. The students who lose marks on IB exam almost never lose them on the calculus. They lose them on the dropped negative sign or a term left behind during the rearranging. So that's the implicit differentiation. I hope that when you look back at chain rule, the product rule, and everything from 5.4 through 5.9, you can now see them all as the same idea, just wearing different clothes. Thanks for watching, and I will see you in the next lesson. This has been Alex.